Oksana, maybe. Okay. Zastavka, yes. And I have a great honor to present Serhii Bardyla. Thank you so much for agreement to present your very interesting research. And please
Oh yeah,
share your screen.
thanks
Share your
for the
screen.
invitation. I'm glad to be back in Lviv, at least virtually. I'll try to share my screen. Okay, that's the last slide, I suppose. Okay. Is it visible?
Is it visible? Ah, yeah, and now it's perfect.
Okay, great.
Mm-hmm.
So, yes, I will speak today about intrinsic topologies and groups. So I would like first to explain what does this strange word intrinsic means. So in this case, intrinsic means topologies which arise from the algebraic structure, which are really generated by algebra. So this is some additional structure which still is generated by the algebraic structure. Because as you know, like the aim of topological algebra is investigate sets endowed with two structures, algebraic and topological, and investigate it simultaneously, like how topological structure implies algebraic one and how algebraic influences topological structure. So in this particular case, that's why I hope this talk suits the topic of the conference. It's algebraic conference, that these topologies will be generated completely by algebraic structure. So it will be really like another description of algebraic structure in topological languages. So let us start with what do I mean by yes, it works. So what do I mean by topology generated by algebraic structure? So first, I will go slowly and I will try to explain everything. If you will have some questions, don't hesitate to ask me at any point. Just stop me and say like the place, name the place, what is non-trivial for you. So let G be a group. So a function f from G to G is called a group polynomial of degree n. So by the way, in blue, I will mark some essential definitions and essential places. So don't be afraid if you see some blue color on the slide. It's not a mistake, hopefully. So f is a group polynomial of degree n if f of x as a function has the following form. So it's like a large product when a0 x to the power of epsilon1, a1, and so on. So a0, an are just coefficients of polynomial, and they are elements of G, of group G, and epsilon I are just powers of x's. They are either 1 or minus 1. So yeah, so this is completely like functions completely generated by algebraic structure. They use nothing except of multiplication and inversion. So they use basically group operations. Yeah, and for to be rigorous, we consider constant functions to be group polynomials of degree 0. So if you have n equals 0, you formally don't have x's at all. So we consider just constant functions a group polynomials of degree 0. So the following definition is essential. So for any group G, we define the group Zariski topology on G. Why the word group? Because we will have further a semi-group counterpart of this topology. That's why, so, but classically it was just Zariski topology. But for this talk, I will call it group Zariski topology. So this topology is denoted by Z plus minus G. Plus minus stands for that we allow plus minus powers of x's. To be clear. So this topology is generated by the sets of the following non-solutions of equation, of the following equation. You see the equation f of x not equals to 1g, and we take non-solution. This is natural because if you consider the set of all solutions of an equation, then usually these sets are closed. But we are in topology working with open sets. We define topologies in open sets. So we just say f of x is not equal to 1g. It's a complement of the set of all equations, which I will call the set of all the complement of the set of all solutions, which I will call the set of all non-solutions. And f is an arbitrary group polynomial. So this way, this is a sub-basis. So you consider all such open sets, and you take arbitrary finite intersections, and then you take arbitrary unions of them. So in this way, the algebraic structure generates us some topology on our group. So now a bit of history. So the group G is called non-topologizable. It's another definition. If the only Hausdorff topology on G which makes the group operation continuous is discrete. So such group exists. They are very ugly. They are very non-trivial. So because usually, like for example, every abelian group is topologizable. So all of them are non-abelian. So so in topological algebra, we investigate topological groups with some topology. For these non-topologizable groups, this is a case when algebraic structure dominates completely topological structure. So you have your ugly algebraic structure, or nice, it's depending from which point of view you look at it, and you have no compatible topology except of discrete, because discrete works all the time. And what proved, so this Zariski topology was basically introduced by Markov, not directly, but indirectly. So he proves that a countable group G is non-topologizable if and only if the group Zariski topology is discrete. So that's again, so you have a very strong algebraic structure which admits no compatible group topology, and this is if only if this algebraically generated topology is discrete. So which sounds natural, despite its very non-trivial result. Good. So what we know about this topology? For every group G, the topology, the group Zariski topology is shift continuous. What do I mean by shift continuous? So the shift, left shift LG X sends to GX, and right shift RG X sends to XG are continuous. And this holds for all G. If you have a topological group, then it's all the time. It's like it follows from the full continuity of group operation. But from this doesn't follow the full continuity. So this is so-called semi-topological group. So now that this Zariski topology, which we just introduced, is discrete, if and only if the identity element is isolated, because you have shift continuity. And to achieve the isolatedness of identity element, it's enough to find finitely many of these subbasic sets whose intersection is 1G. And you can always find it if your topology is discrete. So what I mean is that it really, like to show the discreteness of the group Zariski topology, we need only to find finitely many of nice group polynomials to get the intersection of these non-solutions of the corresponding equations to get 1G. So for real, the discreteness of group Zariski topology is witnessed by some polynomials of some bounded degree. We don't need the whole set of polynomials. We need only some polynomials until, I don't know, some 100 degree. So this motivates the following definition, which is a kind of stratification of full Zariski topology, that still G is a group. Then for each n from natural numbers by z plus minus n of G, it's a topology on G generated by the same things like as in the Zariski topology, but we take not all possible group polynomials, but we take polynomials of degree at most n. So we take just some partial family of group polynomials. So the arguments above, what I tried to explain to you, the arguments above implies that for each countable non-topologizable group, there exists n such that the full Zariski topology is just equals to some partial Zariski topology for some large enough n. And a natural question is what we can say about this n. How large it can be, how small it can be. How large maybe it's worst question, but how small it can be, it's a very nice question. So Olshansky showed that there is a countable group G which is not topologizable, and this restricted Zariski topology is discrete already for n equals 665. So it's like very strange number, but it is what it is. And until now, I probably don't know another example of a non-topologizable group with smaller n. On the other hand, if you move from another side, so we have a theorem of Banach and Protasov. I don't know why it was never published. So maybe Taras Onufrievich will share this information afterwards. So it's a very nice theorem which states that for each group G, the topology Z2 plus minus G is not discrete. So 2 will not work. And so that results inspires the following natural questions which were posed by Dikrayan and Toller. So the two of them. First of them, whether it always holds that for every group G, there exists n such that the full Zariski topology is equal to its small partial part. So you don't need the all polynomials, but you all the time need many polynomials, but until some degree n. And the second question, which is even bolder, that one says that can we move 2 to 3 from for the theorem of Banach and Protasov? Yes, so running ahead, the second question is still not answered by Serhii, which is very surprising. Good. So far so good. If you have any questions again, just please ask me. So this is the first main result of this talk. So and it's by the way a joint work with Luna Elliott, James Mitchell, and Jan Perez. So we answered the first question. So we constructed a countable, even commutative group such that all these topologies that n plus minus g are different for any non-negative integers nm. So that's a full solution of first question. Good. Now we move to the same notions, but for semi-groups, because usually, as it usually the case, if you have something very natural and interesting for groups, you have some counterparts for semi-groups, and people are first studying something for groups and then move to semi-groups and try to generalize it over semi-groups. And it can be generalized pretty straightforward. So let S be a semi-group. Again, we need to define now a semi-group polynomial of degree n. Now we don't have this plus minus ones. There is another case for inverse semi-groups. We have their plus minus ones, but I will not speak about this during this talk. But just for semi-groups, we don't have plus minus ones above x because we don't have unary operation. And we also not necessarily have a unit. But this is not a problem because we can always attach this unit, or if not attached, then just can assume that, okay, we can put our coefficients a0, a1, an. Some of them could be unit. So it's not a problem. And this is a natural definition of semi-group polynomial. And we can define the same Zariski topology, semi-group Zariski topology on the semi-group S similar fashion as for groups. So now we'll be taking set of all non-solutions of the following equations, the set of all x from G, such that f of x is not equal to g of x, where f and g are semi-group polynomials. So note that the difference is that for G, we put 1 on the right hand. But it's not a problem because if you consider this kind of, even for group polynomials, this kind of equation, f of x equal to g of x, we can always move g of x to the left and we just enlarge f of x to f prime of x to make it. We're getting a larger polynomial, but to the right, we get this 1g. So this is like semi-group world. So we don't have this identity to the right, so we have f of x not equal to g of x. But it's still completely algebraically generated topology, which is very natural. So what we can say about it? So one can easily check that the semi-group Zariski topology, semi-group 1 is without this plus minus. It will be easier for you to follow. So the semi-group Zariski topology on every group is always weaker than the group Zariski topology because basically in group Zariski topology, you have more polynomials. You can always have in the semi-group equation of semi-group, the semi-group polynomials, you can always move them to the left and you will represent them as an equation of group polynomial equals to 1g. However, if group is commutative, then we have nothing else, nothing new. So the group Zariski topology is the same as semi-group Zariski topology. This is a consequence of, in case of commutativity, we have a very simple this semi-group group and semi-group polynomials. So you move all the n's to the left, you have only one coefficient, and you have just the power of x. Power can be negative or positive, but it's not the case. It's not relevant because you can anyway. So if you play it like for 1 minute, I believe that you will believe this equality, that for a billion groups you have that the semi-group Zariski topology on a billion groups is the same as the group Zariski topology. So this observation motivated allegedly the following question, which was posed quite recently. So do the topologies, the semi-group and group Zariski topologies coincide for every group G? So maybe we are like in a perfect world and they will be always the case. So, yeah, and if you want counterexample, then you will need to find some non-commutative group, as we already noticed. Good. So we worked on that question with my collaborators, but we were too slow. We preferred to prove more results and less typing. And our competitors, Goffer and Greenfeld, they preferred to prove and type quickly. So that's why we kind of independently answered the latter question, but they published the paper first. So they actually constructed a countable group G, which for this group G, these topologies are different. However, their example is quite technical because it is based on the so-called small constellation theory, the theory which allowed Shelach to construct his famous Shelach group. And yeah, so this is a very technical stuff and not clear to broad audience. Our construction, on the contrary, is essentially more general and provides many relatively easy counterexamples. Moreover, we rarely provides a full class of counterexamples, and they provide only one. So that's an excuse for publishing later this result. So by sim omega x, as usually we denote the finite permutation group, which consists of all permutations with finite support. So what we show, and this is a quite interesting result. So let X be an infinite set and G be a group such that which sits between, it contains the finitary permutation group and full permutation group. So then we have the following. So the risky topology is already strictly weaker than semi-group. The risky topology in this group G is already strictly weaker than the restricted version for n equals 4 of group Zariski topology. And at the same time, this n equals 4 give us already the full Zariski topology. Yeah, so this is quite surprising. So because to generate this z plus minus 4, you use, so this is a very nice place to notice how essential inverses are. So you are allowed to use inverses, but only polynomials of degree 4. And in this case, you get a full group Zariski topology. But if you use arbitrarily long semi-group polynomials without inverses, then you will not get, you can use arbitrary long of them, but you will not get this even Z4 plus minus. Yeah, so in this theorem is based on two pillars of two important results. First one is a theorem of Banach-Horan and Protasov, which actually showed the second part of the theorem, which I mentioned before. So what they showed that still the same setting, X is an infinite set, G is a group such that it sits between the finitary transformation group and full symmetric group. So then we have that Z plus minus 4 is equal to Z plus minus. So, and moreover, they prove that in this case, this topology is very natural. So this is topology of pointwise convergence. If you don't know, generated by the set with UAB, defined as it's written. So, and this is a very nice part because you have a group, you have algebraic structure, and it generates a topology, and this topology is extremely natural. It's topology of pointwise convergence, and if you consider a symmetric group of some set X, then this is the most natural topology you would consider on this group. So and this is for a reason. For a reason is because this topology comes from the algebraic structure of that group. Yes. So moving further, so this is the first important theorem. The second important theorem requires two new definitions. So we have first one is a bit technical. A subgroup G of symmetric group is said to have no algebraicity if it satisfies the following thing. So you have basically, you can fix any set X pointwise by your elements of a group, and any point outside of X you can send to infinitely many places by elements of groups that fixes those elements of X, of S, sorry. Yes, and the second definition is a topological space X is called hyperconnected if the intersection of any two open and empty subsets is non-empty. So this is a quite ugly space, they never Hausdorff unless your space is singleton. So as a prototype for this topology, you can consider for an infinite set, cofinite topology. So topology whose non-empty elements are those with complements, with finite complements. This is an example of hyperconnected space. So what we showed, the second theorem, is that let G be a group with no algebraicity, then for any such group, the semi-group Zariski topology is very ugly. So it's hyperconnected. So it's not even Hausdorff. So this class, probably I should told it before, but this class of groups with no algebraicity, it's essentially larger, but that the previous used in the theorem of Banach and Protasov. So it includes all dense subgroup of symmetric group with respect to the topology of pointwise convergence. So it includes all those groups which sit between the finitary symmetric group and full symmetric group. But it's not only those groups. So you can, for example, the homomorphism groups of any manifold of dimension at least one, it will have no algebraicity. Also, some automorphism groups of some random graph, for example, should also have no algebraicity. Good. So the latter result about this hyperconnectedness for groups with no algebraicity imply a few interesting corollaries. So the first one gives a partial answer to the second question of Declan and Toller, which is still not completely answered, but at least something. So let G be a group with no algebraicity, then this 3 plus minus G topology is hyperconnected and never discrete. So this is a positive answer that for 3 you're not able to get discrete one for groups with no algebraicity. So this holds because this Z3 plus minus is actually a topology is weaker than the semi-group topology. That's again, if you will play with it like a few minutes, you will see how to get from a group polynomial of degree 3 from the equation group polynomial degree 3 equals to 1, you can split it into two semi-group polynomials of some degree with the same set of solutions. And the second corollary, which I also like a lot, so it characterizes as connectedness of restricted Zariski topologies on certain subgroups of full symmetric group. So the corollary states as follows. So let X be an infinite set, we still have the same setting. So G be a group which is between finitary symmetric group and the full symmetric group, then the following dichotomy holds. If n is greater or equal than 4, then you will have a very nice topology, which is topology of pointwise convergence, and it's totally disconnected. So you have a base, it's zero-dimensional. You have a base consisting of closed sets. But if n is less or equals 3, then it immediately starts to be very ugly, it's hyperconnected, which is kind of interesting dichotomy. Good. So let us move to another kind of topologies which are still generated by algebra. So for a group G, the group Hausdorff-Markov topology on G is the intersection of all Hausdorff group topologies on G. So again, it's not directly derived from algebraic structure, but if you intersect all possible group topologies, then Hausdorff group topologies, then you are not no more. You don't rely anymore on topology for real. You really you have some topology which is driven by the algebraic structure, but not direct, not like in the Zariski case. We have again, so Banach and Protasov in the same article shows that Hausdorff-Markov topology over group G is actually the group Zariski topology for each subgroup of the symmetric group over X with the same property. It should contain this finitary symmetric group. So as you can see, it's quite indeed algebraically generated as it's equal to the group Zariski topology. So what we did, we complemented the above result as follows. So we have some weaker statement because we have only on symmetric X, only on the full transformation group of X, but we prove this that the pointwise topology is actually the intersection of all Hausdorff topologies, which turns X into a paratopological group. Paratopological means that you already not require continuity of inverse. And it is essential because methods of Banach and Protasov depends on the Zariski topology essentially. But in this case, if you don't allow inverses, continuity of inverses, then you're not able to use those methods because, as we proved, like the semi-group Zariski topology is for this symmetric group is hyperconnected. So you will not be able to get this result using some polynomials, semigroup polynomials. So we use different techniques. Good. So the group Hausdorff-Markov topology had two counterparts for semigroups. As it usually the case, yes, you have something for groups. Again, you have something for semigroups. So for a semigroup S, you have the semigroup Hausdorff-Markov topology, which is intersection of all Hausdorff semigroup topologies. And you have a semigroup Serhii-Markov topology, which is intersection of all T1 semigroup topologies. For groups, there is no reason to separate these two cases because any T1 group topology is Hausdorff. So we will not have this separation. But for semigroups, it's not the case. Good. So how much time do I have?
You have 2 minutes.
2 minutes. Okay, so I will skip another question then. So we answered another question about this Serhii-Markov topology, and also with competition with Goffer and Greenfeld. However, we did in ZFC. So that's an did in ZFC because we used a very recent result of Pur and Renaud about Shella group in ZFC, and they seems like didn't know about that result. So that's a disadvantage of publishing your article too early. Yeah. So we showed that like for this group of Pur and Renaud, we showed that Serhii-Markov semigroup Serhii-Markov topology is discrete, but group Zariski topology is not discrete. So this is an example of non-topologizable group, uncountable, with non-discrete Zariski topology, which shows that results of Markov cannot be generalized over countable case. And I want to finish with the last slide, which states that one can ask, we always work with like full continuity, saying that the intersection of all topologies which have full continuity, all group topologies and so on. So what if we can move to shift continuous topologies? But we will not have any more non-topologizable groups in that case. So the following result of Zelenyuk states that each infinite group admits a non-discrete Tikhonov topology which makes the shifts and inversion continuous. So for groups, there is nothing to do there in terms of non-topologizability. However, for semigroups, as it usually the case, the situation is different. And for instance, recently, Oleg Lutik, in his recent preprint, constructed a few very, very nice examples of very exotic nature. So he constructed sub-semigroups of the bicyclic monoid, 2 of them. The first one admit only discrete Hausdorff topology with respect to which the right shifts are continuous. So it's like non-topologizable with respect to continuity of right shift, but at the same time, it is topologizable with respect to the continuity of left shift. And the vice versa. There is also another sub-semigroup of the bicyclic monoid, which is non-topologizable with respect to left shift, right, and topologizable with respect to right shifts, moreover Hausdorff topologizable. Yeah, so as you can see, like sometimes in semigroup world, the situation can be completely different. So that's all, and thanks for your attention.